You can see my slides, okay?
Perfect.
Perfect. Okay. So today I want to talk about multi-agent pathfinding and its applications. But before I start this talk, let me just point out that I'm just the person who gives the talk here. Lots of other people have done the work. We have a larger group of students. We have lots of collaborators around the world. They have students. So they did the work and deserve all of the credit for what we are talking about today. So let's get started with the talk here. So it's about multi-agent pathfinding, or MapF. And so during this talk, I will say very often MapF. And whenever you hear MapF, I mean multi-agent pathfinding. So what is multi-agent pathfinding? So we are given an environment like the environment here, and we know exactly how it looks like. Several robots operate in the environment, as shown here. For every robot, we know its current position, and every robot also has associated with it a goal position. And what we need to do is we need to find collision-free paths, one for each robot, that get the robots from their current positions to their goal positions. And that's really an optimization problem. And the objective typically is to minimize either the task completion time, that's also called make span, or the sum of travel times, that's called the flow time. In this talk, I'll minimize the sum of travel times, the flow time. Now, in order to solve this problem, we make often some simplifying assumptions. We take this continuous environment and we discretize it into a grid that consists of square cells. Square cells in white here are unblocked, meaning the robots can enter them. Square cells in gray here are blocked. These are obstacles. We also discretize time into time steps. And then at every time step, a robot is in one of these cells here, and we assume that it fills the cell completely. And then within one time step, it can move to a neighboring unblocked cell to the north, east, south, and west. And it can also wait in its current cell. Now, the important part here is that we need to avoid collisions among the robots, right? That makes the problem difficult. So if we think about, how do we tackle such a problem? Then, well, it's quite easy. We think about, well, what should the state space be? And in this case, the state space here, oops, one too far. The state space here is given by the locations of all of the robots, right? One location per robot. So I'll use this particular situation here to illustrate some of these algorithms that we are talking about. So here we have a grid. There are no blocked cells. We have a red robot that needs to move from A2 here to E3. And we have a blue robot that needs to move from B1 to D4. So here we can ask, what's the start state, right? And in the start state, the red robot is in A2. The blue robot here is in B1. So then we can ask ourselves, well, one time step after that, where can the robots be? And we can enumerate all of the pairs of locations that they can be at. And then we can ask, well, 2 time steps later without collisions, where can the robots be, and so on. That gives us this tree here. And then we can simply search the tree with some best first search method like A*. And that works, right? So that gives us a flow time optimal plan. But of course, this has the problem that the state space here grows exponentially in the number of robots. So it just doesn't scale. And in fact, that is something that we see here. So what we are seeing here is just a diagram that I want to fill in during this talk. What we are having here is the number of robots here. So that's given in log scale. We create an example environment. So we solve multi-agent pathfinding problems on this particular map here with the required number of agents and random start and goal locations. Let's assume that we create, say, 100 of these environments. Here, I'll show how many of these environments an algorithm can solve within a runtime limit of 1 minute. So if we use the algorithm that we just looked at, sort of A* in the joint state space, right? So we see the scaling behavior given by the blue line here. So it doesn't scale very far. And in particular, to take one of these plots and condense it into a single number, I'll always list the number of agents in which we can solve all of the benchmark problems in a minute. So in which we have 100% success rate. And for this joint A*, it is 3 agents. All right, so we can solve very small multi-agent pathfinding problems, but that's just not good enough. And the reason why it's not good enough is simply because the applications that we have in mind require tons of agents. So let's look at some of the applications we have in mind. So this here is in Amazon Fulfillment Center, and in particular, the warehouse part. So Amazon stores all of the goods on special lightweight shelves. So these are the ones that are shown in blue here. So you can see a shelf here. And so let's assume that you order something from Amazon. So for example, a teddy bear. So what happens then is that a robot goes into the warehouse part. It finds a shelf that contains a teddy bear. It uses a corkscrew action, moves under the shelf, makes itself bigger, props up the whole shelf, and then brings the shelf to the perimeter of the warehouse. That's in this case here, where there are human operators, human pickers that take the teddy bear off the shelf, put it into a package to be shipped to you, and then the robot takes the shelf back into the warehouse. So the humans don't need to run around in these warehouses. It's the robot that do all of the work. Now, in this particular case here, if we look at the warehouse part here, then here we see sort of a very small sketch of such a warehouse. In reality, the warehouses are much, much bigger. But we see that we want to use every square inch of the warehouse ideally as utility space. So in other words, to store these shelves. And that means that the corridors that the robots can navigate in when they carry shelves are very narrow. So one robot coming in one direction through the corridor, another robot coming in the other direction through the corridor, the robots can pass each other, right? And that makes for a really, really interesting navigation problem. Now, we talked about, some of these simplifying assumptions that we make in order to solve these problems, but it's interesting that in Amazon warehouses, these are close to being satisfied. Because if you look very carefully at the floor here, then you will see sort of white dots. And I marked some of them here with these red circles. So you could view them as markers, right? Say as barcodes. And they help the robots to navigate, right? So that they don't have any location uncertainty when they move around in the warehouse. And you can see that they really delineate a grid. And so robots do move from grid cell to grid cell without location uncertainty in these warehouses. So these simplifying assumptions are very close to satisfied in Amazon warehouses. Now, but Amazon doesn't just need MapF technology in their warehouses, but also in their sorting centers that are also part of their fulfillment centers. Because what happens once your package is ready with a teddy bear inside of it, it needs to get transported to the right loading dock. And so a package gets put on each one of these robots that you see here, and the robots find the right chute. So these chutes here correspond to loading docks, and then the robot dumps the package into that chute. And again, that's a multi-agent pathfinding problem that needs to get solved. Now, in conjunction with Amazon Robotics, we did a simulation of these sorting centers. And I don't know that might not play very well, depending on how good the bandwidth is at the location where you are at and listening to this talk. But what you're seeing on the left side here is a simulation of the behavior of the robots if they use a very, very simple traffic system. And what I mean by traffic system is simply that we plan for every robot a shortest path from where it is to where it needs to be next. And then we move the robot along the shortest path. Now we need to avoid collisions, of course. And the way we avoid collisions is by using traffic rules, just we use on our streets. So what you can see here, hopefully sort of a little bit, is that the robots bunch up. So we get congestion, just like in our cities, on our streets during rush hour. And that, of course, is not good for throughput. We want to avoid it. On the right, what you see is how the robots behave if we plan for them using a good multi-agent pathfinding planner. And so you'll see that in this case, with the same number of robots, with the same layout, we can avoid these stop and goes. So we get much better throughput. So that's also shown on this diagram here, where on the x-axis, we have the number of robots. So you could view this as the robot density in the warehouse. On the y-axis here, you have the throughput, which is measured in the number of delivered packages shoots per time step. Now, the orange curves that you see here, that's the traffic system that we saw on the left. So you can see that for small robot densities, it works just beautifully. But then at some point in time, you reach a robot density here, right, where we get this congestion, and then the throughput even goes down. On the other hand, using a good MapF planner, you can see that we get much, much better scaling behavior. And that's important because Amazon wants to operate in this blue part here. So they say that per section of a warehouse, say per floor, they want to operate with 800 to 1,000 robots. And this is why if you can develop sort of good high performance multi-agent pathfinding algorithms, that makes industry news as shown here, because potentially that's a game changer. All right, so now that we're all fired up, right, on trying to figure out how do we solve this multi-agent pathfinding problem, not just for 3 agents, but for 800 to 1,000 agents. Now let's talk about algorithms and how we can actually do this. So we want to achieve practicality here. And for that, we need to scale up these algorithms, right? We need to achieve efficiency here so that we can handle 800 to 1,000 robots. How do we do it? Now, the first thing that we should do is we should look at the complexity of the problem, because that tells us something about how hard it will be to develop good algorithms for it. And here I have bad news, because we know that it's NP hard to find make span and fluid time optimal MapF plans, even on planar or grid-like graphs. So that's bad news. And in principle, we knew this for a long time, because we in AI, of course, we study these sliding tile puzzles to death. And if you think about it, right, that's really a multi-agent pathfinding problem where the tiles correspond to the robots, right? And we know that finding optimal plans for these sliding tile puzzles is really NP hard. Now, there were sort of results missing for bounded suboptimal planning. Now, what do I mean by bounded suboptimal planning? So here we don't want to necessarily find a plan that minimizes flow time, but a plan that achieves a flow time that's a user-given factor away from optimal. Right? So that means, you know, we still have a guarantee, but it's not quite as good as finding an optimal plan. But hopefully, if we find a bounded suboptimal plan, then we can do it a little bit faster than finding an optimal plan. Now, there were results missing here. So we filled in sort of one result, but we need more results. So if you're a theoretician, that's a problem that you might want to look at. But sort of our first result here suggests that at least in some cases, it remains NP hard to find bounded suboptimal MapF plans for small suboptimality factors. So what that means really is that when we want to develop algorithms, we have our work cut out for ourselves, because we need to find really, really intelligent algorithms that exploit the problem structure and, despite this complexity barrier, scale up to large numbers of agents. So let's think about how we do this. And I want to start here with optimal planners, see how efficient we can make them. And our planners here will be based on search. And I'll argue in a second why this is important. And then if optimal planners are not good enough, right, then we can go to bounded suboptimal planners and eventually to suboptimal planners that do not make any guarantees. But let's start with the optimal planners here. So I want to describe an algorithm for you. It's an algorithm by our collaborators, not by ourselves, but it's an algorithm that lots of people build on, including ourselves, and that I can describe to you in 2 or 3 minutes. So it's a really simple but very powerful algorithm. Now, I'll use again our example here, where we have this red robot that needs to move from here to here, the blue robot that needs to move from here to here. No cells are blocked. So what we do is we decouple planning for the 2 agents, because single agent planning, after all, is fast. So we do that by finding a shortest path for the red agent here, from here to here, without considering even the presence of the blue agent, right? And so such a path is shown here. And then we do the same thing for the blue agent, shortest path for the blue agent from here to here, without considering even that the red agent is present. That gives us this path here. Now, if these 2 paths don't collide, then we have a flow time optimal MapF plan. We can just return it and we are done. But of course, here, unfortunately, both agents want to be in D3 at time step 4. So we do have a collision, and we need to resolve this collision. So how do we resolve the collision? Well, we just do it by splitting this situation here into 2. In one situation, we say, well, the red agent is not allowed to be in cell D3 at time step 4, right? That avoids the collision. And in the other situation, we say the blue agent is not allowed to be in cell D3 at time step 4, right? That also avoids the collision. Now, if we look at this particular part here, right, then whatever path we had for the red agent beforehand doesn't work any longer because it does not satisfy this constraint, right? So here we need to plan a new path for the red agent. Again, we will ignore the blue agent. It's not there, right? But we now need to satisfy this constraint. And again, we can do this very, very quickly. So find a new path for the red agent, this one here. And then we do the same thing here by finding a new path for the blue agent. So we build up this tree, right? So now we have 2 leaf nodes, this situation and that situation. We use priorities, to pick one of them. Say we pick this one here. And then the process repeats, right? There's no collision among the paths. We just return the 2 paths as a flow time optimal MapF plan. But there is a collision here because both agents now collide at time step 1 in B2. So we split the situation further, right? That gives us a tree. We use a best first search method, sort of an A*-like method to search it. And eventually we will find a flow time optimal MapF plan. So this particular technique here is called conflict-based search. And as I mentioned, it's a good starting point for developing more and more sophisticated algorithms. Why is that the case? Well, let's look at our diagram here that I want to fill in, right? Before, that was the state of the art. But now that we have conflict-based search, the green line here is the state of the art, right? So we scale much better than we could scale before. Unfortunately here, if we look at how many of our benchmark problems on this map we can solve with a runtime limit of a minute, it's still only three agents that we can do that for. So that's a problem, but we do better than before. So now the question is, how can we do even better? So this is where then our work sort of starts, right? I mean, we are trying to figure out how can we exploit the structure of the problem even better than conflict-based search does. Now, I don't want to bore you too much with algorithmic details. So what I'll do here is for just 10 minutes, I'll talk about sort of one particular idea here. And that's just so that if you are interested in getting started in this area, you get a feeling for what it involves to do research in that area. But then I will stop. And after these 10 minutes, we will talk again about multi-agent pathfinding on a very high level, right? And I'll show interesting applications and so on. But for 10 minutes, let's talk sort of technical stuff here. And let's try to figure out, how we can increase the scalability of this conflict-based search even more. So I want to look at what actually happened here, right? So we looked at this node here, right? And there was a collision at D3, and then we tried to resolve it by imposing a constraint, and we had another collision here at B2. So why does that happen? So let's look at our example problem here again, and notice the following, right? The red agent has many shortest paths if we ignore the blue agent and we do not have any constraint yet from its start location to its goal location. For example, right, I mean, this one here and that one here. But no matter which one of these paths we pick, if we also look at the shortest path for the blue agent, then any shortest path of the red agent will collide with any shortest path for the blue agent, and it'll collide in this yellow rectangle shown, right? So initially, right, we had the collision here. We tried to fix that, right, by imposing the constraint. And in fact, we did fix it. Another collision showed up here. We are imposing a constraint to fix that. Another collision will show up in the rectangle, say here. We fix that. Another collision will show up in the rectangle somewhere else. So that means that it will take a bunch of node expansions here in order for us to discover that one of the 2 agents eventually needs to wait for one time step. Now, it's not a problem if the rectangular area here is very small, but of course we can pull the start locations and the goal locations further apart, right? We make the rectangular region larger. So if the rectangular region, as in our example, is 2 by 3, right, we need 7 node expansions, not a big deal. But if the yellow area is 8 by 9 large, then we already need more than 1.5 million node expansions. And that's a big deal, right? Because that takes a lot of time to expand all of these nodes. So ideally, we want to get rid of this issue with one node expansion and notice that at least one of the agents needs to wait for a time step. How do we do it? And here's the idea. So the idea is to say, well, it can't really happen that the red agent leaves the yellow area on an optimal path and the blue agent leaves the yellow area on an optimal path. So what does that mean? Well, if the red agent is not allowed to leave the yellow area on the shortest path, that means it cannot be here at time step 3, and it cannot be here at time step 4. So it cannot be at D2 at time step 3, and it cannot be at D3 at time step 4. And that's what we impose as a constraint. So here, when we impose the constraint, before we said the red agent is not allowed to be in cell D3 at time step 4, but now we impose 2 constraints. At the same time, we see that the red agent is not allowed to be in cell D3 at time 4, and it's also not allowed to be in cell D2 at time 3. And that's what we call barrier constraints, right? Because these constraints here impose a barrier for the red agent to leave the yellow area on a shortest path. And that means that if we plan a shortest path now for the red agent from its start to its goal, not taking the blue agent into account at all, but having to satisfy these constraints, now the red agent will wait for a time step. Right? So with one node expansion, we have now resolved the problem. Here, the red agent will wait for a time step. Here, the blue agent will wait for a time step. So this is really cool. And if you start thinking about this, then we don't just have this situation where we can curb an exponential explosion in node expansions to one node expansion here, no matter how large the yellow area is, but there's similar situations as well. So for example, when 2 agents want to move through a narrow corridor in opposite directions, we get exactly the same behavior. So for one agent to notice that either it needs to wait or take a detour around the narrow corridor takes an exponential number of node expansions. But if we impose sort of the equivalent to barrier constraints, we can do it with 1. And then there's sort of other situations as well. But that raises a problem. And the problem that this raises here is that now you need to have a smart PhD student. So this is Zhao Yang's work. But it takes a smart PhD student to sit there and identify all of these situations and come up with these barrier constraints. And of course, right, I mean, even the smartest PhD student, will have difficulty analyzing very complex situations and even identifying all of these situations. So what you want to do is you want to automatically detect these situations and then automatically design the barrier constraints, right, without humans in the loop. But how do you do this? And it turns out it can be done. And then I want to show you how this is being done. So here we assume again that the red agent will follow a shortest path from its start to its goal, and the blue agent will follow a shortest path from its start to its goal. Now we said that the red agent has many shortest paths available that it can choose from. And this directed acyclic graph called an MDD includes all of these shortest paths. So no matter how we move from top to bottom, say A2, B2, C2, C3, D3, E3 corresponds to the shortest path from here to here for the red agent. And similarly, this MDD here includes all shortest path from here to here for the blue agent. So let's assume that both agents move on the shortest path, so move through their MDDs. I claim that certain node combinations are impossible. So for example, right, it cannot be that the red agent is in this node here, so in location in cell B2 at time step 1. At the same time, when the blue agent here is in this node, namely it is in cell B2 at time step 1. So why is that? Well, it's simply a collision, right? Both agents would be in time step 1 at cell B2. That's a collision. It's not allowed. Now, to show that these nodes cannot happen simultaneously, I put an edge between them. And that's here a mutex constraint, right? Because it shows that there's a mutual exclusion relationship between these two nodes. They can't happen both. And similarly, right, I mean, there are lots of more mutex constraints that I show here via these blue arcs. But now we can also propagate these constraints. And let's look at, say, this node here. I claim that it cannot happen that the red agent is in this node, so at location C2 at time step 2, while the blue agent is at this node. So while the blue agent is at location B3 at time step 2. So why can't that happen? Well, if the red agent is in cell C2 at time step 2, it must have been at cell B2 at time step 1. Similarly, if the blue agent is at cell B3 at time step 2, it must have been at cell B2 at time step 1. But we know that this cannot happen simultaneously because there is already this mutex constraint between them, and therefore these two things can't happen simultaneously either. So that gives us now all of these red arcs that I'm showing here. But now the last step. The last step now is seeing that some of these nodes can't happen at all, independent of where the other agent is. So for example, I claim that this node here cannot happen. So in other words, the blue agent, if it follows the shortest path, it cannot be in B3 at time step 2. Why? Well, because assume that it is at cell B3 at time step 2, then the red agent cannot be at C2 at time step 2 because there's a mutex relationship between these two nodes. But the red agent also cannot be at B3 at time step 2 because there's also a mutex relationship between these two nodes. And so the red agent following a shortest path has nowhere where it can be at time step 2. So that's why the blue agent cannot be at B3 at time step 2. And so in solid here, I show all of these nodes that just can't happen if both agents follow a shortest path. Now let's look at the solid nodes here for the red agent, the ones that cannot happen. Notice that if the red agent cannot be at D2 at time step 3 and also cannot be at D3 at time step 4, the other two nodes can't happen either, right? So we are only interested in the nodes that can't happen, the border nodes that happen. But now let's look at these nodes again, right? So these two nodes. So what they say is that the red agent cannot be at D2 at time step 3, and it also cannot be at D3 at time step 4. And these were exactly the hand-designed barrier constraints, right? So now we can design them automatically, can identify these situations, and we can determine what they should be. So this is sort of the kind of work how you can improve then these multi-agent pathfinding algorithms. It gives you just a little taste of it. You know, there's a whole lot of different kind of work that has been done and that can still be done. It's a good dissertation topic. If you're interested in finding out more about these technical details, then in a little bit less than 12 hours, there will be a MapF tutorial at EMAS that 4 of us will give. So just show up there and we'll tell you about all of these details. So here I want to jump back up, as I promised, you know, to the more high level and just say, well, if you take this technique and other techniques that we have developed and you put it into conflict-based search, now you can go from the green line to the red line here, right? And then you can scale to about 100 agents and get 100% success rate on our example instances here, right? So that's good. We are making progress. And the area has made progress, a lot of progress in the past couple of years. Now, what if we relax the guarantee that we want to give and we go from finding a plan with minimal flow time to finding a plan whose flow time is a user-provided constant factor away from optimal? So that should allow us to scale even more, and that's the case. So you can see this here. Now, of course, you have a trade-off. You can say how suboptimal you want to be at most. And if you want to be at most 1% suboptimal, then you get this violet curve here. You scale to about 400 agents. If it's okay to be at most 2% suboptimal, then you get the brown curve here. You scale to about 600 agents. So now we are getting there, right, where we need to be for Amazon. What about if we relax the guarantee that we provide completely, right? We just want to find a good plan, but no guarantees here on the flow time. Now that used to be a real problem because these algorithms exist, but usually they had very, very bad flow time so that you really didn't want to use them in practice. But now we also have a really, really cool planning approach based on a mix of priority-based search with a large neighborhood search that it gives you actually quite good solutions. And it's this approach here shown in pink, right? It scales to about 2,500 agents. Of course, we don't know exactly what the suboptimality is that we are getting because the optimal algorithms don't scale, but we can compare it against the lower bound, just the shortest travel time for each agent individually summed up, right? And even then, we get good bounds on the suboptimality. Now, remember that all of this was for runtime limit of a minute. Of course, if you use it in Amazon systems, you want to have run these algorithms in during execution. So they have to run in a second or so, right? So there's a little bit more work to be done. But that gives you an idea of the amount of progress that exists in the field. So now let me point out that this is not the only thing that you need to care about scaling up these algorithms, but there are other issues that you need to worry about if you want to field them on actual robot systems. And I want to briefly mention two of them. One of them is that robots often have much, much more complicated kinodynamics than what we saw on these warehouse robots. So we want to optimize and automate all parts of a warehouse, including the parts of warehouses that currently aren't automated. Like we want to do high-speed loading and unloading of trucks in loading docks with multiple forklifts. And we got this idea because we had a visiting researcher from Örebro University, and they have these very, very cool automated forklifts here, right? And so now you need to figure out how you take conflict-based search and make it work in cases where we, in our cars, right, have trouble with, right? Because parallel parking is really difficult. And it turns out you can do it by sort of dealing with continuous time rather than discretizing time. And then you get these very cool, smooth forklift type trajectories. The other thing that you need to worry about is that robots will never execute the plans exactly as intended. The problem that we are having here is that planning will always use robot models that are not completely accurate. So for example, because robots have unmodeled kinematic constraints. So we didn't include, for example, acceleration into our planning models. We could try to do this, but remember, right, I mean, we have enough trouble scaling up by not doing this. But if you don't include acceleration, you have the following problem. Let's assume one robot sits here stationary and another robot, comes full speed at it. So then our planner will think that once the robots are next to each other, they can now move in lockstep. In reality, of course, if you send such a plan to the robots, it will not happen. This robot will sit here. The other robot comes at full speed. This robot still needs to accelerate, right? We don't take into account that it takes time to accelerate. This robot will run into the robot that accelerates and will have a collision. So that's a problem, right? Plan execution will deviate from the plan, but we still need to guarantee robustness in the sense that we don't want to have collisions. So how do we do it? And so here we use the standard strategy that we replan whenever the plan execution deviates from the plan. So clearly, right, I mean, it would be dumb to say just because one robot is a little bit delayed that we want to delay all of the other robots to be able to execute the plan in lockstep. We definitely don't want to do that. Replanning here says, well, whenever the robots are not at the locations we expect them to be, because one robot got delayed, use the planner again to find a new mapf plan from where the robots are now to their goal locations, and then switch to executing that plan. And in principle, that works really, really beautifully. But here we have the plan, the issue that the robots will deviate from the plan quite often. And planning takes a lot of time, as we have seen. So if the robots deviate from the plan every 10 seconds, and then you need to replan, it takes a minute, then robots would be idle most of the time. And that's not good for throughput. We need to do better than this. How do we do it? Well, here's the idea for how we do it. So once we have found a mapf plan, then what we'll do is we'll stick to the paths of the robots that are given in the mapf plan. But we will change their speeds in a very smart way so that the plan remains executable and doesn't have any collisions. So now I need to tell you how we can recalculate the speed quite frequently with several hertz during execution to keep the robots safe. Let me use this particular mapf problem here, where we have two robots on the left that need to move to the right. And the way they do this is that the blue robot here moves into the alcove to let the green robot pass. So the planner will give us this plan here, where the green robot needs to move from E to B to C to D to E. and the blue robot needs to move from B to C to F to C to D. So we take this plan and we compile it into this precedence graph here, where the bubbles correspond to events, namely the event of a robot entering a certain location or being in a certain location. And so arrows here correspond to precedences between events. So an arrow here, for example, says that the green robot first needs to be in A, and then in B, and then in C, and then in D, and then in E, corresponding to the plan. And the same for the blue robot. But we also have these edges here. What do they say? Well, notice that both of our robots here want to be in location C at some time. So here the trick is the insight that a plan remains executable without any deadlocks, even if robots get delayed, for example, if the robots still visit a common location in the same order as they do in the plan. So in other words, here, the blue robot visits location C first, and then the green robot visits it in the plan. And so we need to make sure that during execution, even if robots get delayed, it's still the case that the blue robot visits C before the green robot. And that's what we see here, right? So this precedence here says that first the blue robot needs to be in C, and then afterwards the green robot can be in C. Now you notice also these small bubbles here. These are auxiliary locations. So what this really says is there's sort of some location that's some delta, some parameter delta behind location C, and one here that's some delta before location C. And now we're actually saying that the blue robot needs to have left location C and entered this auxiliary location a little bit sort of behind it before the green robot is allowed to approach location C and enter this auxiliary location a little bit before it, right? And that gives us safety distances between the robots. So now what we do is we take all of these edges here and annotate them with lower and upper bounds on the traversal times. So for example, this edge here, right, we know it'll be traversed by the green robot. We know the maximum velocity of the green robot. We also know the length of this edge, right? It was this parameter delta. And so we can say that even if the green robot moves at maximum velocity, then it still needs a second to traverse that edge, right? So lower bound on the traversal time here is a second. And upper bound here is infinity because we don't have speed minimums which the robots need to move. All right, great. So what we are now having here is called a simple temporal network. And they're very fast algorithms that now determine the earliest arrival times for each robot in each location so that these constraints are satisfied, these bounds that we just imposed on the traversal times. Once we have these earliest arrival times, we can now calculate the speeds of the robots, right? For every robot, we look at the next location that it needs to be in. We know how far this is away from the robot. We know when it needs to be in that location, right? We divide one by the other, and that gives us now the maximum speed with which the robot can move to arrive at that particular location at the earliest allowed time and not earlier. So this can be done very, very quickly using search. So you can run this several hertz. I wrote it down also as an LP, although in practice you wouldn't really use an LP to solve it, just to show that it can be done in polynomial time. Now, let me point out that if you want to evaluate sort of these kinds of algorithms here that show robustness, you need to do it on actual robots, right? Because as we said, a simulator would never be good enough. It would never have the real robot model. But then the question is, how do you do it, right? I mean, if you want to try it out on 5 robots, well, you have 5 robots on your lab. But what if you want to try it out on 800 robots? We don't have 800 robots in our labs. And so here, thanks to our collaborators now at Brown University, we have a really cool mixed reality simulation. The problem here is that if you run this in a simulation, A, the simulation needs to be sufficiently fast, and B, it needs to be sufficiently realistic. And as we said, only real robots are sufficiently realistic. So here it's a blend of different robot models. The yellow robots here make these simplifying assumptions and really do move according to these simplifying assumptions that we made earlier. So that means the motion model is not realistic, but we can simulate them very fast. Now we also have these orange robots. They use a real physics simulator to determine how they actually move, right? So that's a much, much more realistic motion model. but it also takes more time. That's why not all of the robots are wrongish, right? So that we can simulate sufficiently fast. But then even a good physics model, right, is not as realistic as real robots. That's why there are some robots that are running around in the lab and they get projected onto these green robots here. And so the green robots actually move 100% realistic because they correspond to real robots, right? And so that's a way of then evaluating these execution frameworks for robustness. So in my last 4 or 5 minutes, I want to pose a challenge to all of you. So we heard in the beginning remarks, right, that now learning is part of the workshop where it didn't used to be a couple of years ago. And so I have a challenge for you. And the challenge here is, how do we utilize learning for solving multi-agent pathfinding? Now, if we use deep reinforcement learning, for example, we learn a policy. And a policy has lots of advantages. One of them being that, yes, it takes time to learn, but we do that offline. And then online, during execution, right, we can very, very quickly determine a good plan. So let's try to use sort of deep reinforcement learning here. Now, let's look at Deepmind, right? Deepmind taught us how we can learn how to play video games like these old Atari video games using deep reinforcement learning. So we could say, well, we want to pose multi-agent pathfinding as a video game, right? Finding a good path for every agent to move on so that they don't collide and get to the goal locations quickly. That's the video game. And then we can use deep reinforcement learning to solve it. And in fact, we can do even better, right? Because remember, learning is offline. So we can use our planners also to find good plans because time offline doesn't matter. And then we can use a mix of deep reinforcement learning and imitation learning where we imitate these plans from the planners. So we tried this. We used this particular architecture here where we learn a policy for each agent, and then we use the same policy for each agent. Now, what's the input to the policy? Well, for each agent, within its field of view, so depending on where it currently is on the map, it sees all of the obstacles, sees all of the other agents, it sees the goals of all of the other agents, and sees its own goal, right? And then you can determine how large the field of view is. But if you want to keep it small, it could be that its own goal is not within its field of view, and we want it to learn goal-directed behavior. So we also give it a direction vector in the direction of its own goal. All right, so this joint work with Carnegie Mellon University. We trained this for 20 days in a supercomputing center. And I'll show you here on the left an example where the robots here follow a plan that was determined by a good MapF planner. On the right, where they follow a plan that was determined by this learning system. Now, in some cases, it works really nicely. Here, I picked sort of something where the planner is done now. So it was a good, effective plan, low flow time. On the right, eventually, the robots will all get to their goal locations, which I think is really, really cool. But it takes them much longer. So the flow time here is much higher. So at this point in time, end-to-end learning doesn't work quite well yet. And we have also seen this in the NeurIPS Flatland competition. So this was a train scheduling competition where 700 participants from 51 countries participated. And here you see a very small part of Flatland. This was done for thousands of trains in the larger instances. But it's very similar to these warehouse robotics situations where we have a single track, a train moving in one direction on the track, another train moving in the other direction, right? They can pass each other. So it's amenable to multi-agent pathfinding algorithms. Now, it turns out this was joint work with Monash University. Our joint team won that competition, also follow-up competition in 2021. But what's important here, when we look at the leaderboard here, is the techniques that the top performers used, all optimization techniques. And then reinforcement learning was used only by the 7th best entry. And that was nowhere close in score, right, to the top entries. So again, that shows that this end-to-end learning doesn't quite work yet. So how do we use machine learning in our own work? Well, we use it to enhance planning with machine learning, because it turns out that planners use lots of hard-coded decision strategies. So for example, in conflict-based search, if you have several collisions, which one do you want to resolve next? The conflict-based search uses a hard-coded human-developed strategy, but machine learning techniques can do much better. And that means that the resulting planners can be much more efficient or effective. All right, so my time is running out. I'll just show you 3 more applications in joint work with MIT. We are working on multi-arm assembly. So in a joint workspace here, the robots assemble a structure. And of course, they shouldn't collide with each other. It's a multi-agent pathfinding problem to which we can apply these algorithms that you learned about. With NASA, we used to work on airport surface operation. So the idea here is that it's not good if planes taxi all the way from the runways to the gates because it needs lots of energy, it creates lots of pollution. Therefore, in some airports, trains are only towed by these human-driven tow trucks, and NASA was very interested in automating these tow trucks. Of course, here, right, it's a multi-agent pathfinding problem. We don't want to see these planes collide. And the last problem here I want to mention is pipe routing. So here, when you design a chemical plant, often you have 2 locations and you need to connect them with a pipe. So this is a design problem. Why is that a multi-agent pathfinding problem? Nothing moves here, right? And so here you need to see that in a standard multi-agent pathfinding problem, you want to avoid collisions in X, Y, T, T for time. Here, we want to avoid collisions in X, Y, Z, Z for height. In a standard multi-agent pathfinding problem, you want to minimize the sum of the travel distances of the agents. Here, we want to minimize the sum of the pipe length. So you can see multi-agent pathfinding algorithms, perhaps surprisingly, apply to pipe routing. So this is another joint project with Monash University. And that gets me to the end of the talk, the last slide, where I just want to point out again that if you want to learn more about multi-agent pathfinding, which I think is a really, really cool topic, and certainly lots of dissertations can be written in that particular area, then you can attend the EMAS MapF tutorial in a little bit more than 11 hours now. But if you can't attend this, we also put out an information site at mapf.info. You can just type this into your browser, and on the website, I'm showing you here the front page. You find lots of papers, but also video tutorials. You find some of the benchmark instances that people use. You find software that you can use for free in your research, and you find an interesting class project. So if you're a teacher, you can teach it to your students. We provide teaching material, so you can come in and you don't know anything about MapF. We'll teach it to you. There's lots of material, code snippets, completely worked out projects for the students. And if you're a student, you can use it for self-study, although we will not provide you with the sample solutions that we do send to teachers. So let me stop here. Let me thank you again for the invitation, for everybody listening. And if there are any questions, I'm happy to answer them. Thank you.
Well, thank you, Sven, for the wonderful talk. So let's thank our speaker. There was a really fantastic explanation of all the challenges in multi-agent pathfinding. So we have some time for questions, and there is a question in the chat that I'm going to read out from Xian. This is the following. So this question was related to, I believe, when you were explaining how to combine machine learning and reinforcement learning, essentially, with the multi-agent pathfinding. So the question is, this presumes a stationary distribution of problems or domain. Is that the right assumption?
Yes, I mean, so clearly. And so when we actually train, I mean, so just think about, how this is being used in practice. In practice, if you want to use this in a particular warehouse, you even have the map available. And you also know something about the tasks that will come in, right? So from where, for example, you might have to pick up products. So the way you want to use this in practice is by actually, looking exactly at the map that you're having, training only for that particular map, and then looking at the distributions that you have typically for the transportation tasks. Of course, if you do it in research, right? I mean, it is also interesting to look at how far you can generalize, right? Whether you can generalize from one map to the other, right? But in practice, certainly you want to utilize all of the advantages that you have.
Where and the work I will be presenting now may be geared towards applications in those domains, but it's actually, I think, relevant for vast scope of disciplines, because it's about algorithms and it's about methodologies. And essentially, it's about this methodology, the family of methodologies that we call model-based deep learning. In order to understand what do we refer to by model-based deep learning, let's start a bit from the beginning, right? So we're nowadays witnessing a dramatic growth in machine learning, ranging back from the areas where people started investigating brain-inspired computing, and it's now revolutionized many fields. And we're virtually in the scenario where, you know, we're not that close to having our coffee machine beating us in a data science competition. And if we're looking at machine learning, essentially the main revolution is due to the deep learning, which is a sub area of machine learning, which deals with using deep neural networks to solve and to carry out inference. And it has achieved unprecedented success in multiple areas, most dominantly in computer vision and in natural language processing. And the unique characteristic of these more traditional deep learning domains is that the problems there are problems which are very difficult to tackle using conventional optimization methods. What do I mean by conventional methods? I mean model-based methods, and model-based methods are those that rely on knowledge of principled mathematical models. So when I'm saying model-based, I mean statistical model, characterization of the problem, the ability to represent what it is that we're trying to do in a closed form mathematical manner. In many applications and in many areas, we have reasonable mathematical models which we can rely on. Okay, so for instance, in signal processing, in communications, in control, in those areas, we do have established models which one can rely on, and they do describe up to some extent the problems we're trying to solve in a relatively reliable fashion, and we have established algorithms which are designed for these kinds of models. Yet, when we have inaccuracies, when we have mismatches, it is well known that many of those methods which assume perfect knowledge of the underlying statistical model, they tend to fail. So that kind of indicates that relying on data, which is what machine learning and deep learning is mostly geared towards, has its pros and cons, and also relying on knowledge has its pros and cons. And in many applications, specifically signal processing of communications, which are more of my natural domains, we often have both. We have some partial level of domain knowledge in which we're very much comfortable with, and we also have data, and that motivates exploring hybrid techniques, which kind of leverage both principled mathematical models and data-driven inference, and particularly utilizing this new strong tool that we have in our toolbox of deep learning, and that is what we call model-based deep learning. So this talk, I will start by going into further detail about what we mean in the sense of model-based deep learning, after which I will survey methodologies. And for methodologies, I will try to categorize them into the various families of approaches one can use in order to combine data and knowledge in inference. And I will start with what we call model-aided networks. And for there, we'll present the more established methodology of deep unfolding and that of neural building blocks. Then I will discuss the family of methods which we refer to as DNA-aided inference, which can be categorized into structure-oriented and more structure-agnostic and neural augmentation. And I kind of will try to categorize and to put order into ways to combine partial domain knowledge and data in designing of inference rules in a manner which is geared towards both, towards leveraging both. So this is the main focus of this work, of this talk. So let's start with what is model-based deep learning. So obviously it involves model-based, which is knowledge, and deep learning, which is data-driven. And to explain that, I will focus on supervised setups and just kind of recall the notion of inference very briefly. Then I will discuss what is model-based inference versus data-driven inference and kind of try to show them both. Okay, so if I'm using like classic textbook notation, so an inference is just a mapping from some input space to a label space. And by defining this mapping, we also have the inference rule space. And we usually assume that there's some true data generating distribution from which our data is generated. Then by formulating a loss function, we can obtain a risk function, or the generalization error is the expected value over this true generative model, which kind of tells us how good our inference rule is. And our goal is usually to design an inference rule which is the best in the sense of the risk function. And this is exactly what model-based methods try to do, right? We use domain knowledge, we use knowledge of this underlying data generating model, and we formulate an optimization problem. And once we have a closed form optimization problem, we can use the suitable tools from our optimization toolbox to kind of tackle this depending on the specific characterizations of this problem. And domain knowledge can be very diverse. It can be statistical domain knowledge, like we have some kind of a linear Gaussian model. It can be a deterministic domain knowledge, like we also often have in compressed sensing applications. And it is not that ML-based methods do not rely on data. Usually we have parameters which are unknown and must be estimated from data. But the more common method is the kind of a generative approach, where you use your data to estimate your missing domain knowledge and then substitute it and carry out your optimization problem using this missing domain knowledge. And essentially, it looks something like this, right? Once you have that, you have your input, you have your output, you have a concrete, mathematically closed form optimization problem, which actually describes what it is that you're trying to do. And based on that, you come up with some algorithm to solve it. And then it is actually very suitable and very specific to the problem you're trying to solve, yet it requires full knowledge of the full domain knowledge and sensitive to inaccuracies and can be slow. Now, when I'm saying that you need accurate domain knowledge, like in wireless communications, it makes a lot of sense to say that I have full domain knowledge, because I mean, the input-output relationship will be the channel output and the channel input. And we have good models from physics, from wave physics, and from the central limit theorem, which allows us to characterize this relatively reliably. But when I go to computer vision, kind of try to get a joint statistical model for an image of a dog and the breed of this dog, that might be slightly elusive. And on the other hand of the spectrum, there's this the data-driven methods which rely on data. So here, instead of having a description of their problem, we don't have a mathematical description of a problem. We have data. So we cannot formulate the risk function. We can formulate the empirical risk. Obviously, we're prone to overfitting unless we induce some inductive bias. And once we do that, we can formulate our problem as trying to find the inference rule, which minimizes not the true risk function, but the empirical risk function. And that gives rise to generalization issues and overfitting. But the common inductive bias to assume, at least in the deep learning literature, is that of a neural network, which is both highly expressive, can capture very broad range. Essentially, any broad measurable mapping can be captured using a deep neural network. And it also admits tractable optimization using first-order methods such as stochastic gradient descent, in which the gradients can be relatively simply computed using the chain rule of calculus via backpropagation. And it's essentially model agnostic. You don't need to describe your problem mathematically in any form. You just need data, and you're kind of using a generic solver and kind of fit it to the specific task at hand. Now, I'm saying you don't need knowledge, but that's not completely correct, because you do account for some level of domain knowledge in the selection of the architecture. For instance, if I know I'm dealing with images, I would exploit the notions of spatial stationarity and locality in order to use convolutional neural networks. If I know I'm dealing with time sequences, I may prefer recurrent neural networks. But in the end of the day, it's like a kind of a black box solver, which is good for a very wide range of problems. And we're using our understanding of the problem via data to fit it to the specific task. And that allows us to achieve wonderful performance, really unprecedented empirical success. We're generating fake people. We're surpassing human level on identification in classification. Yet it does come with a price. We hardly understand what's going on inside. It takes a lot of time to process, a lot of very highly parameterized models, very heavy models, robustness, generalization. These are all issues which are undergoing research, and they're considered drawbacks of using deep learning literatures compared to very suitable, specific model-based approaches. So let's kind of compare model-based inference to data-driven inference for two specific applications. So the first one is one I'm feeling comfortable with. Okay, let's consider symbol detection in a wireless communication setting. So in that setting, let's say we have a receiver. We have some finite memory channel connecting what was transmitted by the transmitter and the receiver. And the transmitter transmits a set of bits using some constellation, and the receiver has to understand, based on what it observed, what was transmitted to it. Now, since it's a finite memory channel, the classic approach would say, okay, use the Viterbi algorithm. That's a very established algorithm, one of the leading workhorses of wireless communications. It's essentially about dynamic programming, and it requires full knowledge of the underlying channel model, the likelihood of the observations given the input, the fact that it can be factorized, and by using the applying dynamic programming, you can actually compute the maximum likelihood sequence detector, which is very good, but you should have full knowledge of the underlying channel. You need to properly capture it. And if you don't capture it well, you may start deviating. More data-driven approach, that's the one that was proposed, let's say, by Farsad and Goldsmith in 2018, which used the bidirectional recurrent neural network, which exploits the fact that there's temporal correlation, and it probably makes sense to have some kind of a forward-backward recursion. But once you formulated this bidirectional recurrent neural network, it's just training end-to-end. You need a lot of data. It's not super interpretable. And this is like the two edges of the spectrum for this kind of a problem. However, if we can also look at, more computer vision type of problems like compressed image, let's say we have a high resolution image, we're observing a low resolution distorted image and we want to recover it. Now here the model-based approach would be to impose some kind of a model. Let's say I'm imposing that my image is sparse, and then I can approximate the computation of the map rule as the last subjective, and once I formulate the subjective, I can tackle it using some iterative algorithms such as ISTA, and that would mean that I would boil down to these kind of iterative rules, which rely on some set of approximations I made along the way. If I look at more the data-driven approach, well, one can just train a convolutional neural network either in a supervised manner or in an unsupervised manner. There's a lot of work on using deep models for super resolution for compressed image recovery. So once we look at this, we see that there's like a continuous spectrum in some sense, which varies in data, in parameterization as compared to domain knowledge and specificity of the solver. And in the one edge of the spectrum, there's the model-based approaches like Viterbi algorithm and the ISTA algorithm. On the other edge of the spectrum, we have like the bidirectional recurrent neural network model and the ResNet-based or convolutional networks for deep recovery. And that indicates that, well, each of those approaches are very geared towards either using solely domain knowledge or relying solely on data. And that gives rise to the questions whether one can benefit from both partial domain knowledge and limited amounts of data. And if so, how to combine. And this is actually what what model-based deep learning is about. It's about this middle ground, this set of techniques which clearly lie in the middle ground and combine partial domain knowledge and data. And there are essentially two main methods to do that. One is what we call model-aided networks, which integrate model-based methods into deep architecture. So essentially, you infer using some kind of a neural network, but your neural network is not an off-the-shelf one, but is one which is geared, which is suitable for the problem at hand based on your partial domain knowledge. The other family of methods is what we call Data Inference, in which you apply your conventional, your classic algorithm, but you augment it, you empower it, you replace the specific components in it with trainable models. And I will discuss that furthermore in the remainder of this talk. The main rationale here is essentially to benefit from the best of both worlds. So let's start with the methodology, which I call model-aided networks, which aims at designing deep architectures, but which are not off-the-shelf deep models, but one which are suitable for the problem at hand. So yes, this is what we're trying to do. We're trying to use our knowledge of what would have been the suitable solver had we full domain knowledge and design a trainable architecture which imitates and possibly even specializes to the model-based algorithm in some cases. And that would bring us an architecture which is specific to the problem at hand. So essentially, a design approach would say, okay, let's say I have full domain knowledge, what would have been the suitable method? And if I know what's its structure, I can understand whether a reasonable approach would be deep unfolding if it's an iterative optimizer, and neural building blocks if it's based on kind of a block diagram illustration. Okay, so let's start with deep unfolding, because that I think is the more classic way for model-based deep learning. Classic in the sense that it originates back from 2010, which one can consider as ancient history, right, in the deep learning literature. And that is about taking an iterative algorithm, fixing the amount of iterations, and then designing a trainable method which imitates the operation of each one of those iterations. And then you'd have a model which kind of operates at fixed complexity. You know exactly how much iterations it's going to run, but possibly by making those iterations into trainable models, you can improve convergence, you can have something that is interpretable. And compared to black box deep neural networks, you usually have less parameters, less trainable parameters. Now, this is like the main story of deep unfolding, but there's actually more to it. You can actually think of 3 different approaches to implement this deep unfolding methodology. So we know, so since deep unfolding is all about iterative optimizers, let us recall that when we look at iterative optimizers, there's actually two steps, two families of parameterizations. One is what we call the objective parameters, which is how we describe our optimization problem. Let's say, for instance, in the image recovery, the lasso problem, we have our formulation of the lasso objective, and it has its parameters, like the regularization parameter rho and the measurement metrics psi. Now, this formulated task, once this is formulated, I know what's the task I'm going to solve. But also, once I choose the problem I want to solve, there's also the hyperparameters, which are parameters of the solver. For instance, if I'm solving this using proximal gradient descent, which boils down to the iterative soft-thresholding algorithm, then my hyperparameters are the step sizes and the threshold of the step size for the gradient step. And you know, one can think that hyperparameters are usually not that important, right? Because assuming you can run until convergence, then they shouldn't affect the result. But when you run a fixed number of iterations, they obviously affect the result, right? So there's actually three different options to unfold such an iterative algorithm into a trainable model. So the first one would only learn the hyperparameters, namely completely preserve the operation of your model-based algorithm. However, you leverage deep learning techniques such as automated gradient-based optimization in order to optimize the hyperparameters in an iteration-dependent manner, while avoiding techniques which are more cumbersome, like backtracking and optimizing on each step. So you may take an iterative algorithm, you may run it in very few iterations, but by properly tuning the hyperparameters in a per iteration manner and doing it using automated optimization tools designed for training deep networks, you may get something which converges much faster. You can also jointly learn both the objective parameters and the hyperparameters. And by doing that, you end up having each iteration kind of trying to tackle a different objective. Why would you do that? Because that may yield something which is more abstract. And perhaps by having each iteration solve slightly different problem, the overall algorithm after few iterations may yield improved performance. And the third approach would say, okay, I'm deviating from the algorithm. I'm no more longer care about the original parameterization of my iterative solver. I'm just going to design traditional deep layers which are inspired by how the algorithm works. Let's show examples for each one of those options. So for improving convergence, let's consider, for instance, the problem, which is it's a problem in communications, which one has to set how the precoding metrics in a multi-antenna transmitter, and that boils down to this optimization algorithm, which has some achievable sound rate objective subject to some power constraint. And a suitable way to solve that would be using projected gradient ascent optimization, which is definitely suitable for solving this problem, yet it requires a lot of iterations in order to converge. And specifically in wireless communications, we need to run this algorithm once every coherence duration of the channel, namely in the order of milliseconds. We need to run this in the order of milliseconds. So the question is, can we make the algorithm, can we apply the iterative optimizers which we trust, the projected gradient ascent, but make it run much faster? So yes, we can. We can fix the number of iterations and then just treat the hyperparameters, the step sizes per iteration as trainable parameters and just train them from data where, for instance, we can use past channels to optimize. And as we saw, for instance, that allows you to cut by, let's say, a factor of more than 10 in the convergence rate, just by doing that, and you do it offline and then afterwards it runs. But this is for a problem in which we already have a very good optimizer, which we trust, and we only want to make it run faster. Deep unfolding, as was originally proposed by Gregor and Lecon, was proposed for sparse coding, for a sparse recovery. And they dealt with solving the lasso problem, which is inherently a surrogate problem for compressed sensing, because it's already a relaxation of the lasso formulation. So what they proposed was to look at iterative soft-thresholding algorithm, which is a suitable algorithm for solving the lasso problem, and fix a k number of iterations and treat for each iteration the processing as linear layers and the threshold as a trainable parameter. Now, by doing that, you can actually coincide with the original algorithm for a specific setting of these parameters. So that means that you have a very principled initialization. However, the trainable parameters here are both objective parameters and hyperparameters kind of interleaved into one another. So you end up having more abstract model, something that looks like a DNN, but it has a very good principled initialization, because for a given setting, we know exactly that these are Q iterations of ISTA algorithm. Now that kind of motivates the question, okay, when you kind of interleave the objective parameters and the hyperparameters, what you're gaining for it. And this is actually a question that we started looking to it in the context of optimization over discrete spaces. And what we saw is that it actually makes sense to tell the two apart, to learn the objective parameters separately, because by learning, you kind of learn a different objective, but you may learn a different objective for which it is easier for you to optimize. So for instance, you can start with, this would be like your loss surface. So your optimum spot would be here. However, since you're working on a discrete space, you may have to project it to a different value. So it might make sense to learn some different objective, which is optimizing the same discrete point, yet it is also easier to converge to. And then after you do that, you can unfold and train the hyperparameters under the postulated objective. And this is something that we saw and when we kind of looked into specifically also in the context of wireless communication receivers. Now, the third approach to implement deep unfolding would be just to deviate from the iterative algorithm and to kind of abstractify it and reparameterize it into a deep neural network. For instance, we can look at this problem of multi-symbol detection that was considered in the work of Ami Wiesel and co-authors in 2019 called Learn to Detect. And they dealt with this problem that we have here, which deals again with a very simple L2 minimization over discrete space. And they formulated a projected gradient descent for this setting, which were projection essentially the sign operator. And then they designed layers which imitate the operation, and a layer which imitates the operation of the gradient step, and another layer which imitates the operation of the projection, but these are not the same operations. Okay, this is a deviation from the original algorithm. However, you have a deep network which is inspired by how the algorithm you would have designed is solved for that. And it's not completely black box. You understand what are the internal features of this neural network, because the output of each one of those blocks is essentially a next iteration of your algorithm. So you can treat those internal features as estimate which should be gradually refined of the data you're trying to solve, and you can actually account for that in training, and you can make training easier. So here you're kind of already in the domain of the more deep neural networks, but you can use the fact that it's more interpretable to facilitate training. Now, the rationale here of deep unfolding is to take this iterative optimizer and to use the fact that it has like this sequential flow diagram to design a deep neural network based on that, right? But I mean, it's not unique to sequential operation, right? You can do this with every algorithm which can be viewed as a block diagram. If it can be viewed as a block diagram, you can either treat each one of its blocks as trainable and parameterize it or abstractify it, and then optimize the whole thing end to end using automated tools that deep learning provides relatively simply. So for instance, you can treat, again, I'm going to take another problem in communications, that of multi-symbol detection. Okay, and if you look at this kind of a problem, then the suitable method would be to formulate a joint recovery problem, but we know that this one is exponentially solved. It's very difficult to solve. Its complexity grows exponentially with the number of symbols you're trying to detect. You can carry out multiple separate detection problems, and that is here the complexity only grows linearly with the number of symbols you're trying to detect, but it's definitely suboptimal. But there's also the family of interference cancellation methods which operate iteratively, where you estimate and you use your estimates, you estimate separately, you detect separately, but you use your past detections in order to improve your future ones. So one of them is the soft iterative interference cancellation algorithm proposed by Choi et al. in 22 years ago. And that essentially boils down to an algorithm which takes the form of this iterative algorithm, where each one of those blocks here carries out this interference cancellation step, followed by soft decoding, and it uses the soft detection from the previous iteration to facilitate the detection of the future iterations. And essentially, each one of those blocks of the tree carries out soft iteration and interference cancellation, soft decoding is essentially can be viewed as a classification task. So one may actually replace it with trainable classifiers, abstractifying it while maintaining the overall operation, the overall block diagram of the algorithm. And by doing this approach, you can actually preserve the operation of the model-based algorithm. You understand what are internal features, so you can also account for it in training. You can either train end-to-end, but you can also account for the fact that you know what are the outputs of each block. And by doing that, you can also further improve compared to model-based algorithms. You can even apply interference cancellation in regimes in which the model-based algorithm is not applicable. For instance, where interference is not known how, it is not that clear how you can cancel it. But here, because you abstractify this operation, you can actually learn to do that. So the approaches that I've shown so far, they're all about taking an iterative or a model-based algorithm and using it to design a trainable method, which is kind of trained end-to-end. The other approach is what we call DNA-aided inference, which uses deep learning not as our inference rule, but as a means to augment and to empower an existing algorithm which is suitable for the problem at hand. For instance, if we know that we have this algorithm which is suitable, but we do have some subtle points, some part of it which we don't know how to compute or we're not comfortable with, we can just learn it and possibly still be able to learn the whole thing end to end. It's kind of an overall discriminative model. And then you benefit from your gains of your model-based algorithm in terms of complexity, performance, suitability for the problem. But you can also do that in a trainable manner while overcoming shortcomings. So actually, in order to understand what are the different families to implement that, it all depends on what you know of your problem. Like, what is the missing piece of the puzzle that you do not know, and that if you had known, how would you have solved the problem? And that kind of allows you to divide into what we call structure-oriented and neural augmentation, where the available knowledge you have is the structure of your data. So you have algorithms which are suitable for this specific structure, but you still need to account for model mismatches and parameters which you don't know. And the other approach is when you don't know your signal domain, you don't have a prior, you need to know a regularizer, and that goes to what we call a structure agnostic DNA-aided inference. Now, I will elaborate more on what we call structure-oriented, which deals with problems where you do have good statistical structures. They can be obtained from physical characteristics, from system operation, from your understanding, from approximations, though different disciplines have different levels of approximations, but they do allow you to get a good characterization of you have a relatively good partial domain knowledge, but there's details which are missing, and the devil is always in the details. But you do have structures in advance, and those kinds of structures can be exploited, which allows you to, let's say, to learn the missing model subtleties. Now, one approach, now this is not a very systematic methodology, so I'm going to show two examples here. One example goes to the Kalman filter. Okay, so Kalman filter is one of the most fundamental algorithms in signal processing and in control, and that deals with the tracking of dynamic systems. So we have observations, we're trying to track some dynamic state which evolves in time. And we know that the state and the observations are related by what's called a state space model, which is divided into the state evolution model and the observation model. And this is a very common representation for problems of localization and tracking. And actually, it originates from the need to put the Apollo program, the Apollo spaceship, in trajectory around the moon, where it had to sense its own location. And this is where the Kalman filter, I guess, became most well known. And the Kalman filter deals with a specific setting of a state space model, which is a linear Gaussian state space model, where the state evolution and the measurement model both takes a linear Gaussian models. And for this kind of scenario, it actually allows you to carry out the minimum mean squared error estimate in a controllable complexity, which only uses, it doesn't use the all past observations, it just uses the current observation and the previous estimate. And it is essentially comprised of a prediction step, which takes the previous estimate and predicts the next estimate and the next observation, and an update step, which requires all the statistical moments and compute this measure called the Kalman gain, which allows you to combine the estimate based on your current observation and the prediction based on your previous prediction. And yeah, that worked relatively well for Rudolf Kalman. That became one of the most celebrated algorithms. Here is receiving the Medal of Science from President Barack Obama. So if we think about applying Kalman often in practice, you do need full knowledge of the state space model. And the state space model, while usually some parameters of it are known. For instance, we know state evolution corresponds to the motion equations from kinematics. It's those noise signals which kind of encapsulate the stochasticity, which we often don't know. So that means that in practice, we often have an approximation of the state space model. So we may be able to do the prediction step, but doing the update step, the computation of the common gain may be elusive. And that implies that perhaps instead of just estimating these parameters, you just might learn to carry out the Kalman gain in a trainable manner and even abstractify it perhaps with a neural network. And then you'd end up having a model which preserves the operation of the Kalman filter while only using trainable models to learn the specific computation of it, which is that of the Kalman gain. Now, why is it so good? I mean, if you're comparing let's say the extended Kalman filter to the Kalman net, we know that the latter is model agnostic. It does not require imposing any model of the noise, and it can learn from data to cope with mismatches. And it also preserves the real-time operation of the Kalman filter. But the gains are not only in performance. The fact that you preserve the operation of an algorithm and you trust allows you to carry several more benefits. For instance, you can improve runtime, both compared to state-of-the-art deep learning models, but also compared to the model-based algorithm, which requires a good deal of computations to compute the Kalman gain. It requires matrix inversion on each step. And once you replace it with a trainable model with a fixed complexity, you may be able to not only improve performance, but also in runtime. And you also end up using a relatively low complex architecture. For instance, this specific model, we were able to implement it on an autonomous racing car, which had to estimate its velocity. I think it was 20 times a second in 200 hertz or 300 times a second. And it had a relatively mismatched state space model, which captures how the currents it receives from the wheels are related to its velocity. So model-based approaches had some errors due to those mismatches. Deep learning approaches, which they tried in the past, just didn't work. They worked on simulations. They were incapable of implementing them on the vehicle control unit. But when you operate in this hybrid model-based deep learning manner, you can actually have something which is of low complexity, and they actually managed to implement it on the vehicle control unit. And it was actually awarded the AI awards in the Formula Student Germany competition in 2021. And also, the fact that you preserve the operation of the model-based algorithm does just imply performance and complexity. It also means that you understand what's going on. And if you understand what's going on, you can, for instance, extract uncertainty. You can relate the internal features into measures of confidence, let's say covariance, and that actually allows you not only to estimate, but also to predict how accurate your estimate is, which is usually a complicated thing to do when you're dealing with black box architectures. The fact that you understand the features can also provide you means to train in a supervised manner, because for instance, you can predict your next observation. And it also naturally extends to other variants of Kalman type filters. So the fact that you're implementing something not just purely data-driven or purely model-based allows you to gain not only in performance, but also in other less measurable benefits. Another example I'm going to show for this kind of methodology relates to Viterbi detection, right? If I mentioned earlier, the Viterbi algorithm as being one of the leading workhorses of wireless communications, and it deals with symbol detection in finite memory channels. So we have a transmitter, it transmits symbols from a finite constellation, and our receiver has to map them to map its channel output into the estimate of the estimated symbols. Now that is a basic operation of a digital receiver, but specifically since it's a finite memory channel, that implies that the likelihood function takes this Markovian structure, which can be factorized. It can be just represented using a factor graph, specifically a Markov chain, and that allows you to represent the transmitted symbols as state, and you have this kind of a state space, this kind of a state machine. And it was proposed by Andrew Viterbi in the late 60s. He ended up founding Qualcomm. Here, just like Rudolf Kalman earlier, he also was awarded the Medal of Science, but him from President George W. Bush. And the Viterbi detector is essentially about dynamic programming. It decomposes the likelihood function of the observations given the desired information into building upon the fact that it can be factorized as a Markov chain. So it factorizes it, and then on each observation, it computes the log likelihood function, and it maintains and gives the score to each possible combination of the channel inputs, which could have led to this observation. And using these cost functions, it essentially carries out dynamic programming by preserving passes along this diagram, which we call the trellis diagram, but it's essentially dynamic programming. And that allows you to both compute the maximum likelihood sequence detection, also infer in real time, because with very high probability, your paths will coincide with a different state once you have the memory steps forward. And so that's a very useful algorithm. However, it requires you to know exactly to compute those log likelihoods. But once you compute the log likelihoods, you have the log Viterbi algorithm. It's just a set of algebraic manipulations. So if one can just replace the computation of the log likelihood with a trainable model, and that's not a super complicated task to do, it's much more simple than just detecting this block of symbols given the entire block of symbols. You can even have a trainable architecture which actually learns to carry out the Viterbi algorithm without knowing the channel and can cope with very abstract models. So by doing that, you can actually implement Viterbi detection in a data-driven fashion while completely preserving its operation. So these two examples I've just showed are for what we call a structure-oriented DNA data inference. There are also other approaches which I will only briefly mention. Okay, so what we did so far, we replaced those domain-specific computations, the computations which we didn't know or were not comfortable with in the model-based algorithm. We replaced them with trainable architecture with deep network. Another alternative, which is coined neural augmentation, preserves the operation of the original algorithm and acknowledges the fact that it may not be that good because there's model mismatches, but it also combines an external model for correcting it, for adding correction terms. So the external trainable model is not about inferring, it's about correcting and making the model-based algorithm, which we know has mismatches, operate better. And it was shown that this kind of approach allows you to both infer more reliably and use more compact and faster trainable models compared to if you use the trainable model just for the inference task itself. So if you look at it, like you have the missing piece of the puzzle, it's not like you're replacing the missing piece of the puzzle. You kind of try to correct it using an external trainable model. So what we did so far was on settings in which we knew we had a good algorithm, we just had some details which were missing. I guess another very popular application of model-based deep learning uses not the fact where you know your structure of the algorithm, it's the structure of the signal which you don't know and you're trying to overcome. For instance, often in practice, we're dealing with the question of what makes a signal belong to our domain of interest. For instance, how can you tell if a matrix or a tensor represents a natural image? So earlier we discussed, okay, so maybe you can represent it as a sparse in some domain, let's say the wavelet domain, but that's just, an approximation. And a lot of work dealing with model-based deep learning, they kind of try to capture these complex domains using trainable models and then substitute into a suitable model-based optimizer. So it's actually very suitable for those regularized inverse problems where you can either learn and use deep learning to actually learn the regularize the prior, which is what's called deep priors, and then you replace your prior with a trainable model. And alternatively, you can apply the optimizers which requires this prior. Let's say you're using ADMM, and then this prior becomes a proximal mapping, and then just replace this proximal mapping with a trainable model, and that's what's called plug-and-play networks. But on that, I will not go into that in detail now. I will, though, conclude this talk. So what we showed here, what we discussed is that, yes, we do have a very powerful toolbox, a data-driven toolbox, which is deep learning, and it brings forward data-driven tools. Yes, it's not magic. And especially in domains where we have good level of domain knowledge, it makes a lot of sense to combine it into this hybrid paradigm of model-based deep learning, which provides various systematic frameworks for combining knowledge and data, for augmenting optimization algorithms, for improving optimization in terms of performance, convergence, and robustness. And I do believe that this categorization I propose here, its goal is to facilitate future design and to show that one can combine this in various different types of problems. There are many areas which are dominated by model-based algorithms. We'll talk about communications, about radar and control, And the way I see it, the potential of these hybrid approaches, just the tip of the iceberg. I do recommend you guys, those of you who are interested, we do have 2 survey articles. Both are available on archive. The second one, which is the most recent one with Janina Eldan and Stephen Boyd, is more geared towards optimization. The first one, model-based deep learning with Jay Wang and Alex Demakis, is more geared towards generic inference problems. Do encourage you guys to look into that. Let me know feel free to contact me if you have any questions, ideas. And with that, I will conclude. I want to thank you guys for attending my talk, and let me know if you have any questions or anything.
Okay, thank you, Neil, for this great talk. It's very interesting and very inspiring. And me myself, I have some questions, but let's ask the audience first. So, if anyone has any questions, you can either just speak out or put your questions in the chat. So yeah, maybe let me ask my first question. So I really like this idea that you build this spectrum and put this model-based deep learning in the middle. So I'm just wondering, like in general, like given a problem, what kind of features do you think, like if the problem have this kind of features, then can be a good fit for this type of model-based deep learning methods?
I would ask you 2 questions. First, do you have a good model-based algorithm for this problem? Okay. And if you do, what are its shortcomings? It's usually easier to look at your algorithm which is suitable for this problem, and then kind of, because this is at least the approach that I'm tackling. If you don't have a good solver, you're already, the only thing you know how to do is to take data and to train abstract models, then you have less to gain from here. So this would be the question I would ask, or like, how would people have solved this problem before the deep learning era? And then, look into the solver and kind of try to improve that. I would also ask the question, what are the, even if I have a good algorithm, I have an optimization problem. It's a closed form, it's full domain knowledge. I can actually write down my optimization problem. What makes it difficult for me to solve it? Is it the fact that I needed to operate quickly? Is it the fact that, I do have some steps which are complicated? I have a complex regularizer, which I don't know how to deal with. These are the questions I would ask. And for those, by kind of pinpointing what is the challenge, this is, I guess, where you can understand where you can gain most by a proper augmentation and a proper combining with trainable models, and particularly leveraging deep learning, because deep learning is not just about this neural network. It's a lot about automated optimization and using data to automate models. Okay, so I do think that's one of the key gains here.
Yeah, that's interesting. So I know, like for some problem, you may have very good, say, models, but usually those models are expensive, like expensive to compute, like in real time. And is your method also like good for those kind of problems? Like you can somehow abstract your original model and then use deep learning to fit in those details.
Yeah, well, I guess it's specific to the problem, but in general, yes. I think in some of the examples I propose are essentially about that, right? Essentially about taking a problem which is difficult, maybe too abstract, and you just need to replace this component which relies on this abstract mapping with either some trainable features, or just take your algorithm and apply it for instance, like I didn't talk a lot about deep priors, right? Deep priors that I have here, or about plug and play networks, but this is just what it's about, right? You have a complex regularizer, which you have an optimization problem, you have a challenging regularizer to deal with. So, I mean, you may require you to do some very complicated stuff in order to compute it, but maybe you can train some kind of a surrogate model, a different model through which you can optimize, and then you replace this deep model, this complicated regularizer with this surrogate model you trained offline, maybe in a supervised manner, and now you can implement your optimization problem in a faithful and in a relatively fast manner. So this is like these are the 2 methodologies. I didn't elaborate a lot here.
Okay, yeah, thanks. Another question from the audience?
I mean, I guess, Nir, well, thanks for the talk. I guess, like a question that naturally arises here is whether this methodology would be suitable also for optimizing under discrete structure. And in a sense, I may know what is your answer here, approximated, but sometimes that's just not enough. So just wonder, what are the limitations? I'm just trying to understand where should we start thinking, okay, we can actually use an integration of deep learning and optimization and just recur to plain optimization methods.
Well, that's a good question, because when you deal with optimization over discrete domains, then the question is, I guess, how would you solve it currently? Okay, because also, doing optimization over discrete domains is challenging regardless, right? So some approaches would say, okay, you kind of do some optimization over a continuous domain, and then you do projection every now and then. So some of the approaches here are essentially about that, the optimization over discrete domains. So I do ask, the question, I guess, that has to be asked is, how do you solve it? How do you currently solve it without augmenting this deep learning? So in some cases, yes, deep learning can be very beneficial. For instance, all the problems that I showed about digital receivers, the Viterbi algorithm, the soft interference cancellation algorithm, the multi-symbol detection, these are all optimization over discrete domains. Okay, so in those cases, yeah, it makes a lot of sense to do that, and mostly in terms of complexity, right? Because optimize over discrete domains, computational complexity grows exponentially with the search space. So it does make a lot of sense in those areas. But if I would say that for learning kind of surrogate models, learning surrogate models which map from a discrete value to some continuous values, and doing it with a deep network, that would be hard, because it's usually like, deep networks are not designed for discrete inputs. So at least they work by gradients, which kind of ignores the fact that your input is discrete. So that may not be necessarily a good idea. I'm not saying it's such a bad. I know that people have done this in some cases, and it was shown to have good performance. But I think of specific problems in communications where I saw people doing that. But I would say it's less natural.
And like another question that in a way it's related. Have you noticed any relation with the dimensionality of the problem and the ability of learning good surrogates or good model-based approaches?
Well, I do think that if you go black box then the curse of dimensionality also hurts you, right? If you just apply a deep network, then obviously the fact that the dimensions grow make you need to, for instance, you need to train each time your dimensions grow, and you need more data. It becomes harder for you to train. So it's not a unique to hybrid approaches. However, the hybrid, if you have like some kind of some algorithms, they deal with growth in dimensionality in a manner which is does not scale in the scaling complexity is less dominant. Like for instance, the interference cancellation algorithm I showed earlier, the complexity of it does not grow exponentially when you increase the number of tasks you're working with. And I would also say that in the end of the day, deep networks cope with very large dimensionality inputs, right? If you think about it, you apply deep networks to large images. These are very large tensors. So I wouldn't say that this is a very big problem. And I would actually say that if you're designing in a hybrid approach, you can actually benefit from it. You may actually be less severely harmed by high dimensional signals. This is my perspective, but it's all, of course, dependent on the specific problem.
Okay, yeah, we're right on time. So thanks, Neil, again for this great talk. We're so happy.
Thank you guys for the invitation. Thank you very much.
Yeah, thank you. So let's move to the next part. So our second session. So here we will have 6 contributed talks, and each talk will be allocated 15 minutes. So we will have a pre-recorded talk that I will share my screen to show. And after each talk, we will have the authors to answer questions. So let's start with our first talk. First, stop recording.